Hello, everyone. It's a pleasure to be here. My name is Bilal, lead application scientist of QBLOX, and I would like to talk to you about our scalable qubit control and readout electronics, which are fully integrated. So for an easy start, QBLOX is a spin-off from QTech, based in Delft, the Netherlands. Since our spin-off in 2018, we are stably and constantly growing. Our team now has reached to 80 people. And since then, we have been supporting many labs all around the world. So together with our partners and collaborators in Delft and all around the world, we are happy to be contributing into a successful quantum ecosystem. So what is our mission? Here is a very known graph. On the x-axis, the number of qubits, y-axis, the error rates. And in 2023, we are roughly here, very quickly approaching a higher number of qubits. And there are two main goals in the industry currently. So one is to reach to NISQ era, and the other one is to reach fault-tolerant quantum computing, where the quantum advantage can be exploited. So as QBLOX, we provide solutions for today for scalable qubit tuning, and these solutions will enable you to run NISQ algorithms in the near future. And we are also contributing into projects for fault-tolerant quantum computing. So where do we stay in this big picture? So here is the known figure, quantum chip at the bottom of the stack, living in the cryostat for superconducting and spin qubits. And there are room temperature electronics and the software. So QBLOX starts with the abstract idea of an experiment that can be represented as a quantum circuit. And then, of course, it's transferred into a Python code that can be understood by the electronics. And in the end, the pulses are executed at the outputs of the electronics where qubits will see. So QBLOX sits in the room temperature part of this full stack. So how is our equipment is built up? To explain the fully integrated architecture, what you see on the screen is an example army of electronics that people have used to control about 20 transmon qubits. So it consists of many AWGs, readout analyzers, IQ mixers, and so on. So this set of electronics can now be integrated into a single 19-inch rack. So our system, our cluster mainframe is fully integrated. It is scalable and modular. So what do we mean by modularity? We have 4 different modules, and we have separated them into 2 different frequency regimes. One is the baseband regime. So the 2 modules that you see on the screen have inputs and outputs from 0 to 400 megahertz. And we have 2 other modules that can directly input and output in the RF domain from 2 to 18.5 gigahertz. So these 4 modules allow us to configure and, if necessary, reconfigure the system for the needs of superconducting qubits to do single qubit gates, 2 qubit gates, multiplex readout, and so on. It can be used for spin-based qubits for all the functionalities and operations needed for these systems. And it can be used for optical setups such as ND centers and trapped ions. So it's a modular architecture, but we want our electronics to act as a monolithic system. And this is managed by our proprietary sync and link protocols. These are hosted by the backplane, which also has a digital architecture. So the sync protocol allows to synchronize all the outputs and inputs in the cluster mainframe below nanosecond accuracy with a picosecond jitter. And the link protocol allows fast scalable feedback. It's the distribution of the measurement outcomes for active reset type of operations or for quantum error correction. So here we provide all-to-all connectivity, meaning that up to 80 control channels can be linked to up to 40 input channels within the same time window of roughly 350 nanoseconds. So analog performance is very important for us. I'm not going to go into detail for the time being, but we strive to provide very high spurious-free dynamic range for the RF signals, very good phase relation between different output and input channels, very low 1/f noise, and great temperature stability, which is the drift value shown in the bottom right part. So apart from the hardware, of course, we have software solutions. And for this, we have 2 different layers. One is Q1ASM. This is our assembly language, in a way, for the Q1 sequence processors. So the Q1ASM allows you to control the FPGA at the very lowest level without going into detailed FPGA programming or VHDL programming. So that's the low-level access. In a way, it's non-intuitive if you look at it from the physics side, but it allows you to control, very fine-tune your parameters in the electronics. And on top of this, we have Quantify, which is a complete software package. It does basically everything for you. It does measurement, orchestration, data analysis, data acquisition, and so on. So this is open source, but professionally maintained by us and our partner Orange Quantum Systems, and it's based on QCODE's parameters. So any other hardware in the field which has QCODE drivers can be used with this Quantify software. So we are also part of some key projects. We are working on real-time decoders to reach for fault-tolerant quantum computing. We are part of Quantum Internet Alliance to connect Europe over quantum networks. So we are partnering with academic labs and industrial partners. We develop and provide hardware to them. And we are also partnering with Kilimanjaro in Spain to integrate a quantum computer in Barcelona Supercomputing Center. So with that, I would like to finish my talk. Please feel free to reach out to us via hello@qblox.com or via my email bilal@qblox.com. Thank you very much.